Welcome to Lecture 3 of the course Sustainable Energy Management and Efficiency for Data Centers. In this lesson, we will dive into the main topic of this course, energy efficiency in data centers. We will examine how to measure energy efficiency and which are the factors that influence it. Understanding what drives the energy consumption of a data centers is the first step towards identifying how to improve efficiency. There are 6 main factors influencing data centers' energy efficiency. They can be divided into 2 categories, internal and external. Let's look first at the internal ones: IT equipment, cooling system, and temperature control. As we have seen, the highest component in the energy consumption of a data center is the IT equipment itself. Several technical characteristics determine IT consumption, starting from the installed IT capacity, which measures the total computing potential of the facility. Secondly, the level of utilization of the IT hardware has a strong influence on the overall energy use. In many data centers, particularly smaller or enterprise-scale ones, a significant fraction of servers remain underutilized. Virtualization, multi-core processors, and workload management can reduce the number of physical machines needed, boosting computing performance. Hyperscale data centers, designed for large-scale workloads, typically achieve higher average utilization rates, up to 50%, while smaller facilities may operate below 20%, pointing to significant inefficiency. Another key factor is the idle power, which represents the energy used by the equipment when not performing active tasks. Reducing idle power is also a target for efficiency. In modern servers, idle power has dropped from around 60% to about 35% of rated power, reflecting substantial technological improvements. Cooling systems represent the second major contribution to energy consumption in data centers. Since the IT equipment generates heat during operation, maintaining optimal temperature and humidity levels is essential for reliability and performance. Some of the inefficiencies arise from the heat transfer losses in poorly insulated pipes and ducts, as well as from the uncontrolled mixing of hot and cold air in the server's room. Techniques such as hot-cold aisle containment, improved airflow control, and better zoning can improve cooling effectiveness. Free cooling technologies, which leverage external environmental conditions, and liquid cooling, which provide targeted thermal management, are gaining popularity. Temperature control strategies also impact the energy use. Raising the set point for the data center's internal temperature can reduce cooling demand. The thermal gradient between the indoor and the outboard temperatures drive the cooling load. Data centers' temperatures between 20 and 25 degrees, with acceptable ranges from 15 to 32 degrees, are recommended. Let's now analyze the external factors affecting energy efficiency: site selection, building structure, and power supply. The geographic location of a data center has a direct impact on its energy requirements, particularly for cooling. Areas with high ambient temperatures and humidity levels demand more energy-intensive cooling systems to maintain the thermal conditions necessary for reliable IT operation. Natural disaster risks, political stability, local infrastructure, labor availability, and electricity costs also play a role in the selection process. Data centers located in cooler climates often benefit from free cooling strategies, where outside air is used to reduce the need for mechanical refrigeration, leading to substantial energy savings. Another important factor is the power supply and distribution system, which includes the uninterruptible power supply units and associated conversion losses. UPS systems ensure continuity of power during outages and are critical for maintaining uptime. Moreover, the design of the electrical infrastructure, including cables, lands, and transformers placement, affect transmission losses. Over long distances, losses of up to 3% can occur due to resistance in conductors, making compact and well-structured layout more desirable. The structure and design of the building also affect energy efficiency. Factors such as the insulation materials, window-to-wall ratio, building orientation, and airflow management determine how much external heat enters the facility, and how efficient internal heat can be removed. Good architectural designs help to reduce the thermal loads and enables more efficient operation of the HVAC systems. After understanding the technical and operational drivers of energy consumption, the next step is to evaluate how efficiently a data center uses its energy. A wide range of metrics have been developed over the past decades, each with a specific focus and area of applicability. These metrics can be grouped into 3 main categories: those based on energy conservation, those related to eco-design and sustainability, and those incorporating security considerations. Among energy conservation metrics, the most important is power usage effectiveness, introduced by the Green Grid in 2007. PUE is the ratio of total facility energy consumption to the energy used by the IT equipment. An ideal PUE is 1, indicated all energy goes to computing tasks, with no overhead. In practice, enterprise data centers often have a PUE values around 2, while efficient hyperscale data center can achieve values below 1.2. PUE is useful for tracking improvements over time and benchmarking across facilities. However, it does not account for the effectiveness of the IT work performed or the environmental context. To address some of the limitations of the PUE, various extensions have been developed. Partial PUE applies the same principle to individual subsystems or specific zone within a data center, offering localized insights. Design PUE provides an estimate of the expected PUE at the design phase, incorporating local environmental conditions and intended operation parameters. A related metric, data center infrastructure efficiency, is simply the reciprocal of the PUE and represents the percentage of the energy delivered to the IoT equipment relative to the total energy consumed by the facility. In evaluating the efficiency of a data center, it is essential to consider metrics related to the HVAC systems. One of the most important is the coefficient of performance, which measures the efficiency of cooling system by expressing the ratio between the useful cooling output and the electrical energy input required to produce it. Another metric is the HVAC system effectiveness, which measures the ratio of the annual IT equipment energy to the annual HVAC energy. The less efficient the HVAC is, the more energy it consumes, which means that the HVAC system has greater need for optimization. While infrastructure metrics like PUE and COP are essential for assessing facility-level energy use, it is equally important to evaluate how efficiently IT equipment performs computing tasks. To this end, growing attention is given to metrics that measure computing efficiency. Server compute efficiency and data center compute efficiency focus on the performance delivered per watt, either at the CPU level or across the entire data center. These metrics help to quantify how efficiently energy is being converted into useful computational work. IT equipment energy efficiency is another indicator that helps to quantify both how efficiently IT resources operate and how effectively they are used. It is computed by the proportion of IT equipment's total rated work capacity and the total rated energy of the IT equipment. Beyond energy conservation, eco-design metrics have been introduced to capture environmental performance. Carbon usage effectiveness measures CO2 emissions per unit of IT energy, making it a direct indicator of carbon intensity. Water usage effectiveness, computed as the ratio between the annual site water usage over the IT equipment energy use, assesses water consumption. Finally, green energy coefficient is used to measure the proportion of green renewable energy used in the total energy consumption in data centers. Finally, some metrics incorporate security requirements, especially in contexts where uptime and data protection are paramount. For instance, the electric energy usage effectiveness extended metric adjusts standard efficiency evaluations by factoring in security-related energy costs, aiming for a more balanced assessment. In conclusion, improving energy efficiency in data centers requires a multi-dimensional approach. It begins with understanding the technical and environmental factors that drive consumption, from the geographic location and power infrastructure to cooling strategies and IT utilization. Building on this understanding, operators and designers can deploy a wide range of metrics to evaluate performance, benchmark progress, and guide investments. This lesson concludes the first module of the course, which provided a foundational understanding of data centers and their energy dynamics. We began by exploring what a data center is, the different types that exist, and how their role has expanded in the digital age. We then examined the core components that make up a data center and analyzed how each contributes to the energy consumption. In this final lesson of the module, we delved into the key factors that drive energy use and reviewed the main metrics used to assess energy efficiency. With this foundational knowledge in place, the next module will shift focus to practical strategies for improving energy efficiency in data centers. We will explore design techniques, operational best practices, and emerging technologies that can help reduce energy consumption while maintaining performance and fostering sustainability.